Welcome to the debate. Today we're diving into the really fast-moving world of time series forecasting. Specifically, we're looking at this exciting new wave of foundation models, which are heavily inspired by the big successes we've seen with large language models, LLMs. And I think the big question in our field right now is, well, can we actually build a single, really powerful model, one that forecasts reliably across all sorts of different data right out of the box without needing specific training for every single new data set? We call this zero-shot performance. So the central debate for us today really revolves around TimesFM. Does its unique architecture, and it is unique, with that decoder-only transformer and this novel patching strategy, does it really represent the most robust and universally applicable approach for this zero-shot time series forecasting? Or do these very specific design choices come with inherent trade-offs, maybe suggesting we still need, well, a broader range of modeling paradigms for truly universal application? My position? I believe TimesFM marks a really significant shift. It optimizes for both performance and efficiency in this zero-shot realm.
Okay, I appreciate that perspective, but I lean a different way. Look, while TimesFM's achievements are certainly impressive, I'd argue its highly specialized design, powerful as it is, introduces some inherent limitations. These design choices, in my view, they leave considerable space for alternative methods, especially when we think about the vast nuances of real-world time series data and, well, the full spectrum of forecasting challenges.
Well, my position, as I said, is that TimesFM's architecture brilliantly adapts the foundation model idea from natural language processing over to time series analysis. It's delivering state-of-the-art zero-shot performance and doing it with remarkable efficiency and really truly broad applicability across incredibly diverse time series data. So at its heart, TimesFM uses a decoder-only transformer design. This is much like those advanced LLMs that generate text word by word, right? But here, it's trained efficiently to predict the next segment or patch of time points based on all the ones that came before it. And this structure allows for parallel processing across long stretches of data, which is absolutely vital for speed and for scale. Now, a critical innovation here is its input patching strategy. Instead of feeding individual data points one by one, TimesFM breaks the time series into these discrete, non-overlapping patches. You can almost think of these as time series tokens. So for example, a common setup might group 32 consecutive data points into one patch. That's your input patch len equals 32. Each patch then goes through a specialized input block, a residual block actually, which transforms it into a compact numerical representation, a vector of size model dim. And importantly, we add a special marker, a positional encoding, PEJ, to indicate its position in the sequence. So you get something like TJ equals input residual block of yitj 001 minus mitj plus PEJ. This whole tokenization approach, it drastically reduces the amount of information the transformer has to process directly. That makes inference much, much faster and crucially improves overall forecasting performance. I mean, this isn't just some minor technical tweak. It's really what makes these powerful, large models feasible for, say, real-time forecasting. It changes how quickly businesses can react and strategize. Another really key feature is its ability to generate longer output patches. So, unlike many language models that predict just one token at a time, TimesFM can predict a much longer sequence of future time points from just a single input patch. Imagine predicting, say, 128 future points. Output patch len, or H, equals 128, from an input patch of 32 past points. Input patch len, or P, is equal to 32. This is incredibly important because it significantly cuts down the number of iterative autoregressive steps needed for long horizon forecasts. Fewer steps mean less error accumulation and, critically, better accuracy. The output layers then map these output tokens OJ back to predictions, like ypj plus 1 dot pj plus h equals output residual block OJ. The model's training is also incredibly flexible, thanks to this patch masking strategy. It uses random mask sampling, which basically exposes the model to all possible context lengths during training, from just one patch up to the maximum context window. This ensures it's adaptable to varying input sizes you find in the real world, not just fixed multiples of the patch length. And the loss function? It's primarily mean squared error, the MSE, for point forecasting. So train loss equals 1n sum MSE of ypj plus 1, pj plus h, ypj plus 1, pj plus h. This whole meticulous design has allowed TimesFM to achieve near state-of-the-art zero-shot accuracy across diverse benchmarks. Think Monash, DARTS, the Informer datasets. It often outperforms even larger LLM-based forecasters like LLM Time, despite being much smaller, around 200 million parameters. And the latest iteration, TimesFM-2.5, offers up to 25% better performance, uses a massive 16K context length, and does it with half the parameters that really showcases its efficiency.
Okay, that's certainly compelling, but I'd frame it a bit differently. While TimesFM's zero-shot capabilities are, yes, undeniably impressive, I believe its specialized architecture and its pre-training choices, efficient though they may be, introduce inherent limitations. These become particularly apparent when we start talking about, say, covariant integration, interpretability, and this goal of truly universal applicability across the full spectrum of time series challenges. My first reservation is really around this fundamental challenge of, let's call it, time series grammar. You know, unlike natural language, which has clear words and grammatical rules, time series data just doesn't have such explicit, universally defined structures. So patching, in this context, it feels more like a pragmatic adaptation, maybe a useful heuristic, but still a heuristic. There's an ablation study in the paper that's quite revealing here.
It shows that while an input patch length of, say, p equals 32 data points is described as a prudent choice, using smaller patches like p equals 8 can make training 3 times slower.
This highlights, I think, a non-trivial design constraint. Finding the optimal patch length involves a trade-off, right? Between computational cost and maybe capturing finer details. It hints that this tokenization isn't necessarily a universally perfect fit for all time series characteristics. And crucially, as you touched upon, TimesFM is not pre-trained with dynamic or static covariance. This is a significant limitation in handling external factors. I mean, so many real-world forecasting tasks are heavily influenced by external variables. Think about holidays affecting retail sales, promotions driving demand, economic indicators influencing financial markets, factors that go beyond just the univariate time series itself.
Right.
Now, while the paper does suggest workarounds, like running a separate linear regression on the residuals at inference time, or maybe fine-tuning the model with covariates, these steps, they fundamentally detract from the promise of a purely zero-shot, out-of-the-box experience. They demand additional effort, additional complexity, that while traditional statistical models or other specialized deep learning models often integrate more intrinsically. Then there's the interpretability deficit. Deep foundation models like TimesFM, they often operate as black boxes, especially when you compare them to traditional statistical methods like ARIMA or exponential smoothing. Those older models, they give you clear, understandable parameters. They can tell you why a forecast might have changed.
Now, TimesFM relies on post-hoc methods like logo or shape. These are techniques that try to explain a model's prediction after it's made by tweaking inputs and seeing how the output changes. They only partially mitigate this issue. In high-stakes applications, understanding why a forecast is being made can be just as critical as the forecast itself. This lack of inherent transparency, that can be a major concern. And finally, while the pre-training data scope is vast, you mentioned the OC100B time points from Google Trends, Wikipedia page views, plus synthetic data like ARMA processes, seasonal patterns, trends, step functions. Its heavy reliance on these, let's say, web-centric sources might introduce specific biases.
These could limit its generalization to domains with fundamentally different underlying data generation processes, or maybe frequencies that just aren't well represented in Google searches or Wikipedia traffic. The fact that an ablation study showed a performance drop when they removed the synthetic data, well, that suggests the real-world data alone has gaps or isn't sufficient to capture all the necessary patterns the model needs. So ultimately, while TimesFM clearly excels, its performance is often described, even in the paper, as close to state-of-the-art, which implies, that specialized models, things like PatchTST, DBAR, NBeats, When they are explicitly trained on target datasets, they can still be competitive or sometimes even superior. It challenges this idea of a single best solution for everything.
Okay, but I'm not quite convinced that the critique about time series lacking a grammar fully captures what patching achieves here. Look, while language has clear tokens, words, patching ingeniously creates these discrete units that transformers can actually work with effectively. We're not just, crudely segmenting the data. We're creating chunks that potentially represent meaningful temporal patterns. A patch of 32 data points, for example, it becomes a kind of fundamental block that the self-attention mechanism can then learn relationships between. And the empirical results really do validate this approach. Choosing an input patch length like 32 isn't arbitrary. It's presented as a carefully determined balance, a prudent choice balancing performance and training speed. The studies even show that using longer output patch lengths, like 128, actually leads to better mean absolute error performance. That proves its effectiveness in capturing temporal dynamics over longer horizons. The way these patches are transformed using that residual block and then marked for position, PEJ, provides the transformer with a rich local context it can then globally attend to. I think this is a very robust form of representation, and it fundamentally enables the large-scale learning we're seeing.
I suppose I come at this from a slightly different angle. While patching certainly makes time series tractable for transformers, yes, I still question whether it truly captures let's say, the continuous, fluid grammar of time series quite as effectively or as nuancedly as linguistic tokens capture language. A word, has a fairly well-defined meaning and role in a sentence. A patch of, say, 32 time points, while useful, still feels like a heuristic chunk. And those ablation studies on input patch length, P, are telling, I think. Opting for P equals 32 is, as you said, framed as a computational and speed decision, but the fact that smaller patches, like P equals 8, which might capture more fine-grained patterns, can be 3 times slower to train, well, that suggests you pay a steep computational price if you want that finer granularity. That's a significant trade-off, isn't it? It implies that this specific tokenization might not be universally optimal for all types of time series characteristics, especially when you have data with really diverse temporal granularities playing together. It means the choice of patch length is inherently a compromise, and maybe that middle ground, that P equals 32, isn't always the perfect fit. And even the output patch length, each, has trade-offs mentioned. If it's too long, handling short series becomes tricky.
But the zero-shot approach itself, that is a truly powerful feature. It completely redefines accessibility and forecasting. By pre-training on this massive and diverse corpus, and we're talking hundreds of billions of time points, O100B, from sources like Google Trends, Wikipedia, and yes, carefully generated synthetic data covering seasonal patterns, trends, armor processes, TimesFM learns fundamental generalized temporal patterns. This broad learning means it can forecast effectively without needing explicit covariate information during pre-training. And that significantly lowers the barrier for users, right? For organizations that maybe don't have the resources or the deep expertise to curate rich covariate datasets and then train complex, specialized models from scratch. The model learns to map directly from past observations to future predictions, making it incredibly versatile and potentially impactful for much broader application. It's sort of about democratizing sophisticated forecasting. I'm sorry? I just don't quite buy that it's truly out of the box for many real-world high-value scenarios. The model's fundamental inability to directly incorporate covariates during its pre-training, that remains a major functional limitation in my eyes. Take demand forecasting in retail, a classic example. Without integrating dynamic covariates like promotional calendars, holidays, or even static features like store location or product category, the forecast is inherently incomplete, almost certainly less reliable.
The paper itself acknowledges this limitation, right? It suggests solutions like running a linear regression on the residuals afterwards, or, significantly, fine-tuning the model with covariates. But these extra steps, they fundamentally undermine the pure zero-shot benefit. They mean the model isn't really plug-and-play for many practical, critical applications. It requires extra work, extra expertise. Furthermore, the inherent interpretability challenge of these deep models, it just doesn't go away. For applications demanding clear causal insights, this is still a barrier. Knowing that demand will increase is one thing. Understanding why it's increasing, maybe because of a specific promotion, which traditional statistical models can often reveal, is entirely another. So how do you see it being adopted in high-stakes industries, maybe finance or healthcare, where interpretability isn't just a nice-to-have, but often a regulatory or core business necessity?
That's a valid concern, absolutely. But I think the efficiency and the scaling benefits of TimesFM are precisely what make it a potential game changer for widespread adoption, even with those considerations. We're discussing a model with only, 200 million parameters? That's significantly smaller than your typical multi-billion parameter LLMs, yet it achieves comparable, sometimes superior zero-shot forecasting performance. And the training cost is remarkably low. The paper mentions the largest 200M parameter model takes just about 2 days on a fairly modest 16-core TPU v5e setup for 1.5 million iterations. This efficiency translates directly into accessibility. It makes advanced forecasting techniques available to many more organizations, maybe smaller ones, that couldn't afford the massive compute for traditional large models. And importantly, the studies clearly show that errors consistently decrease as you provide more computational power, more flops. This isn't just a theoretical hope, it's validated scaling. It means as resources grow, so does the model's performance potential. It makes it a practical, accessible solution for a vast array of forecasting needs, arguably far beyond what traditional, often resource-intensive models could offer to the average user.
Okay, I agree the efficiency relative to huge LLMs is genuinely impressive. No argument there. However, you often describe its performance, and the paper does too, as close to state-of-the-art. That phrase itself implies a gap, doesn't it? For applications where maximal accuracy is absolutely paramount, maybe even a fraction of a percent matters, well, specialized, supervised deep learning models, things like PatchTST, NBeats, or DeepR, which are explicitly trained on specific target datasets, they often offer superior accuracy. Or perhaps they have built-in assumptions, inductive biases that really suit a particular type of data, leading to better performance in that context. The fact that PatchTST, for instance, which also uses patching but is trained supervisedly, performs similarly to TimesFM on certain benchmarks when explicitly trained, that kind of underscores this point. So while TimesFM's efficiency is a huge advantage, arguing that a tiny fraction of costs makes it universally superior might be a bit misleading. For certain high-stakes problems, even a marginal improvement in accuracy from a more specialized, albeit perhaps more expensive to train model, could yield substantial business value. In those cases, dedicated training isn't an unnecessary burden. It's a potentially valuable investment. Don't you think there are definitely scenarios where that incremental accuracy justifies the greater investment in specialized training?
I'm not convinced that focusing solely on that potential gap truly captures TimesFM's utility, especially when you consider its straightforward and flexible inference process. I mean, once it's trained, the model uses this autoregressive decoding, very much like LLMs generate text, to produce forecasts for really any horizon you need. You give it the historical data, it predicts the next segment, the next patch, then it uses that prediction, combined with the original history, to forecast the segment after that, and so on. This iterative process is highly intuitive, and it gives users incredible flexibility. You're not locked into predicting only a fixed horizon. And what I find truly groundbreaking about the recent TimesFM-2.5 advancement is how it pushes this even further with that massive 16K context length. That allows it to process and condition on even more historical data, potentially capturing longer-range dependencies. And remember that clever patch masking strategy used during training? That ensures the model learns effectively from all possible context lengths it might encounter, making it incredibly robust to varying input sizes when it's actually put to use in the real world. It really is designed to be versatile for how users need to interact with it day to day.
That's a compelling argument for its flexibility and usage, certainly.
But what about the inherent caveats? The paper itself explicitly states, and I quote loosely here, that similar to LLMs, there could be inputs on which the model does not perform well or hallucinates. That word hallucinates is quite strong in a forecasting context. Now, for critical use cases, the recommendation is for using it in a human-in-the-loop fashion or alternatively do a wide range of testing or fine-tuning. Doesn't that suggest that this model, despite its impressive generalizability, still requires careful validation, potential intervention, maybe significant guardrails, that directly impacts its out-of-the-box utility in sensitive contexts where an erroneous forecast, a hallucination, could have pretty significant consequences? So while the autoregressive decoding provides flexibility in setting the horizon, the potential for error accumulation over many steps, even with longer output patches designed to mitigate this, it can't be entirely dismissed, can it? Especially if the model might occasionally hallucinate in unpredictable ways on certain inputs. The need for additional testing or potential fine-tuning for reliability inevitably reduces its immediate plug-and-play value for those critical tasks. So, how do you reconcile that inherent risk, that potential for hallucination, with the promise of easy, out-of-the-box forecasting?
Look, I think TimesFM truly represents a significant advancement. It successfully translates the foundational model paradigm, which has been so revolutionary in NLP, to the domain of time series forecasting. Its decoder-only transformer architecture, that clever patching strategy, P equals 32, H equals 128, etc., and the extensive pre-training on that vast corpus, all of this enables highly effective zero-shot performance and impressive efficiency. This opens up entirely new avenues for scalable and accessible forecasting solutions across just a huge range of diverse domains. It's really about taking sophisticated AI and making it genuinely useful, more practical for a broader range of practitioners and businesses than ever before.
I agree that TimesFM's achievements are notable, definitely pushing the boundaries of what's possible in zero-shot time series forecasting. However, its specific design choices, particularly around the, let's call them persistent challenges of covariate integration, the ongoing quest for better interpretability, and acknowledging the fundamental differences between language data and temporal data, these highlight complexities that are still very much with us. These trade-offs, they underscore that truly universal models, if such a thing is even the right goal, might require even more sophisticated designs down the line, or perhaps, more likely, that hybrid approaches and specialized, domain-specific models will continue to play a really crucial role in addressing the full spectrum of time series analysis effectively. Ultimately, TimesFM shows us that while foundation models are incredibly potent for time series, the quest for a truly universal forecaster means we're still balancing that raw predictive power against crucial practicalities like interpretability and handling contextual data effectively.
Indeed. And I think the work on TimesFM undeniably deepens our understanding of how to apply these powerful foundation models beyond their original NLP domain. It showcases immense potential, while also, as you rightly point out, illuminating the complexities that remain in designing models capable of addressing the full spectrum of time series analysis with ideally optimal performance, interpretability, and flexibility.
Couldn't agree more. It's a field just rich with innovation and ongoing challenges, and this particular model contributes significantly to that ongoing discussion. I'd certainly encourage our listeners to, dig into the technical details, the math, the empirical results presented in the paper themselves. It's the best way to form their own conclusions on the implications of these specific design choices for whatever forecasting needs they might have.